at any point, once a tree is built, you'd predict the test observation by passing it down the tree, obeying each of the splits. It'll end up in a terminal node, and then you'll use the mean of the training observations in that region to make the prediction. Let's look at a slightly bigger example, a cartoon example in the next slide. First of all, in the slide, we show in the left panel here a set of regions that couldn't be achieved by this process. So this one here could not be achieved because these aren't boxes that were obtained by sequentially splitting the data repeatedly, whereas the one on the right can. If you look at the one on the right in conjunction with the tree on the bottom left here, you'll see that the first split was made at T1. So there's T1 over there, and that was a vertical split, right, that broke this region. We've got two variables, x1 and x2 here, into a region to the left and to the right. So that's a partition. Then we have a split on x2 at T2. So that is this split over here where we divided that box into two. And so that takes care of the left. We got region 1 and region 2. Then on the right-hand partition that we had by splitting T1, we split x1 again at T3. So we make another vertical split here that partitions, let's draw these in. And so that's a split at this internal node over here. And so that makes region 3 on the left. And on the right, we're going to do one more split, and that's at T4 on variable x2 that divides that into 2. So you can see in the sequential greedy fashion, we've subdivided the space, which is just two variables here, into 5 different regions. Now, at each of the terminal nodes, we are going to approximate the regression function in this case by the mean of the training observations that end up in these terminal nodes. So what that means is if you have a test observation and you want to come and predict it, you're going to start at the top and you're going to query what's its value for x1. If it's less than T1, you'll go to the left, otherwise you'll go to the right. Likewise, you answer each of the questions at each of the internal nodes, and you're going to end up in one of these regions. And then your prediction is going to be the mean in that region. So as a function, you can actually represent it nicely, because it's just a two-dimensional function, by this picture that we've got on the right here. And so it's a piecewise constant function. It's piecewise constant. You can see here the slices. Let's see. This will be T1. Is this slice over here, and this will be T2. And this function is constant in each of the regions. And that's how we're going to represent our function at the end of the day.
Okay, so we've seen how we grow a tree. The question, one question arises is how large should the tree be? When should we stop growing the tree? Well, one possibility would just be to grow as large a tree as possible, right? At the extreme, we could, for example, have a tree that had one observation in each terminal node or leaf. But that's likely to overfit the data, producing poor test set performance. I say, why? Well, I guess it's kind of obvious, right? If you have a tree that's so large that each observation has its own terminal node, it's going to have training error of 0, but it's going to be adapted to that data very much, and it's going to overfit. When you give it new test data, you're probably going to have a quite high error as a result. So not a good idea to build as large a tree as possible. Another possibility would be to stop early. In other words, just keep splitting until it looks like no split helps in some sense in terms of reducing the residual sum of squares, the criterion we saw before. But it turns out this strategy can be too short-sighted. In other words, we'll very often stop too early because it looks like no good split is available, but actually if we kept splitting, we'd see a better split farther down the tree. So it turns out that a better strategy is actually to grow a large tree, stopping only when a rule like, for example, a typical one that's used is a terminal node has to have no fewer than 5 observations, say. And then with this large tree, which is probably too big, we prune it from the bottom to produce a tree which a mid-size. It's got it tries to balance bias and variance, and hence have lower prediction error than either the single node tree or the extreme tree that has one observation. One node per observation.
So a very bushy tree has got high variance in.
Right, it's got high variance.
It's overfitting the data.
Yeah. Low bias, but is overfitting and probably not going to predict well. So actually, so what's done in the CART software, for example, or the tree library in R, which we'll see, is this idea of building a large tree and then pruning it back. And the framework for that is called cost complexity pruning, or weakest link pruning. So for that, we do something actually very much like the lasso we saw for regression. We have an objective function, which is the fit. And remember, the fit we're going to measure in terms of the sum of squares of observations, are the response around the assigned terminal nodes. So our terminal nodes are R1 through Rm. I'm sorry, Rt. The number of terminal nodes we're going to denote by this notation looks like an absolute value, but this means the number of terminal nodes in the tree T. So this is the sum of squares of observations around the mean of region M, which is one of the terminal nodes, and we add them up over all the terminal nodes. So we want a tree which has small variance, but we also want to counterbalance the size of the tree. So we put a penalty on the total number of nodes in the tree with a penalty parameter which will estimate by cross-validation. Again, this is very much like the lasso, where we had a sum of squares of regression, and we penalized the sum of the absolute values of the coefficient, which is complexity. So we want the coefficients to be small to avoid overfitting. Here we want the size of the tree to be small to avoid overfitting. Okay? So cost complexity pruning is going to kind of find the best value of alpha by cross-validation, and then we're going to pick the subtree in the tree, the large tree we've grown, that has the smallest value of this criterion. So it's summarized in the next slide. Well, sorry, this actually just says what I just said. And again, yes? Oh, okay. So here's the summary of the tree growing algorithm. Again, this is not something that you would normally have to program yourself, because software which is available, for example, CART or the tree software in R, it does all this cross-validation process for you, but it's good to see at least once what it's doing. So we build a large tree with a very simple stopping rule. Again, for example, we stop it when the number of observations in a terminal node is some minimum number like 5. And then we prune the tree to find the best subtree. And for that, we need to get an idea of the cost complexity parameter, the best trade-off between fit and tree size. So for that, we use cross-validation in this similar way that we've used it before for regression. We divide the data into k parts, k being maybe 5 or 10. We set aside one part. We fit trees of various sizes on the k-1 parts, and then evaluate the prediction error on the part we've left out.
Oh, so that's clever. The whole thing's controlled by alpha then. Alpha decides how big the tree is, and you use cross-validation just to pick alpha.
Exactly, right. And so we choose the alpha, and we'll see cross-validation curves in a few slides, but it's going to tell us a good idea of the best value of alpha to trade off the fit with the size of the tree. Having chosen alpha, we then go back to the full tree and find the subtree that has the smallest.
So you mean the tree grown on all the training data?
Exactly. So let's see what this looks like for the baseball data. So for illustration, we actually took the observations, divided them into a training set of 132 observations, and the remainder 131 in a test set, because we want to compare the cross-validation error, what we're going to get, to the test error on the separate test set, just for illustration. We build a regression tree on the training set using cross-validation and get an idea of the best cost complexity parameter alpha using 6-fold cross-validation. And by the way, 6 may seem like a funny number, but that's just because 6 divides into 132 exactly. So this was the full tree before pruning. So remember, we saw the top part of this tree before, right? We saw the top split and the right split, and this had all been pruned away. But now we're seeing the details of how we got to that 3-node tree. Here's the large tree that we get, the only rule being that the size of the we don't split a terminal node that has fewer than, say, 5 observations. And that gave us this tree with how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? But probably not all these are predictive. Right?
Why are some of the arms of the tree long and some short, right?
Good question. Tell me why.
It's because the early splits, which have caused a big decrease in the sum of squares, they're depicted by long arms, and then as we get down deeper, the incremental improvements get smaller and smaller. So that's depicted in the way the tree is represented here.
Was that your idea, or who thought of that?
Not me. It's a good idea, though.
So it's whoever the author of the tree growing program in R is. Yeah. Okay. So here's the result of cross-validation, which is going to give us the pruned tree. So what do we see here? Well, we see along the horizontal axis tree size, which is the alpha parameter. So as we vary alpha, it's in one-to-one correspondence with tree size, right? If alpha equals 0, there's no penalty to tree size. So we get the largest tree that we fit, which was about 12 terminal nodes. As we crank up alpha to be bigger and bigger, it puts more and more penalty on tree size, until eventually we're forced to the left-hand side here. We have actually there's just one node. There's no splits at all. So we're seeing the extreme from the full data set to the 12 terminal node tree. And let's look at the green curve is what we get from cross-validation. And it's minimized at around 3 terminal nodes, okay? Well, the training error, I should have said this first, as we expect, this is, of course, we know we can't use training error to choose a cost complexity parameter, because the more we fit, the better it's going to look. And we see that here, right? The more we fit, the lower the error. So cross-validation, on the other hand, we fit for a while, it's happy with the splits, and then it looks like it's overfitting, just increasing variance and not helping prediction error. The test error, which we can evaluate here because we've set aside a separate test set, it's roughly tracking the CV curve. It's minimized maybe around the same place.
So it looks like about 3 terminal nodes is good, which was the first tree we showed.
Exactly. So it's on the basis of this graph that we drew that 3-node tree.